Yeah, well, thanks for the introduction. And again, thanks for joining me. So my talk will be on what I call physical idealism. So let me begin with a single slide that kind of summarizes my main thesis. So in a way, I really argue that our standard view of the physical world is wrong. Well, not quite wrong, but only approximately true in some sense. So I will argue in this talk that in order to solve some foundational problems, and also some practical problems, we need to take a more idealist perspective. So what does idealism mean? Well, if you look it up, then idealism is just a word for a very diverse group of views. These views have in common then they typically regard some notion of mind, whatever that means, as more elementary or more primary and not matter so much. Now, I should clarify here that when I talk about mind, I basically mean information theory. Information, for example. So for me, in this talk, I will not talk about consciousness or qualia or what we believe or know or feel. So for me, this is really, so I will present really a rigorous mathematical approach that's based on information theory. I should also say, since this is a new approach, I may of course be completely wrong. It may be completely nonsense, perhaps. But what I can perhaps promise is that I think this is really fun. I think it's fun to think about the world in these terms and to speculate what it could mean that the world behaves in that way. So here's the plan for today. I will begin by presenting very briefly a couple of conceptual puzzles from the foundations of physics and why I think that they challenge our standard view of the physical world. I will also tell you what I mean by the standard view in a couple of slides. In the second part, I will sketch an alternative view, basically a theory that kind of is in the idealist spirit. In some sense, in this approach, an information theoretic notion of mind is fundamental and the external world is emergent in some sense. The third part, I will show you how in an approach like that, we can understand objective reality as a kind of emergent statistical phenomenon. An approximate phenomenon, and since it's only an approximation, we will run into a couple of very fun and new phenomena, like something that I call probabilistic zombies, for example. So we'll tell you what that is in part 3 of the talk. And in part 4, I will give you an example to show you how an approach like this can dissolve some of the conceptual puzzles that we have. The Boltzmann brain problem. So some of you may have heard of that, or maybe not, but I will briefly introduce this. So typically we think that there is a world, an external world, some kind of universe that evolves in time according to physical laws. And then we're somehow a part of that world. So when we think of ourselves, say myself, for example, and whatever I see at the moment, whatever I remember, whatever makes up myself, yeah. So technically think of all the locally available information where you are. Then we think of that this basically comes from, or it follows from, the state and the evolution of the physical world. And so more concretely, what this means is that when you want to predict, then we apply a kind of standard methodology. A standard methodology means when I, or you, say I want to predict what happens to me next, then I use physics first to predict the evolution of the world. And then I locate myself inside the world somehow. So maybe I do not have to model the whole universe because the laws of physics are local, but maybe I model the room or the planet or whatever is relevant for me, and I use the laws of physics. Then I say, but now I'm here. And so hence, due to the laws of physics, due to what's happening around me, that's what I see. All right. Now, I will show you a few puzzles that arguably tell you that this methodology is inadequate in some cases. So this methodology doesn't help us solve a couple of problems and answer a couple of questions that we would like to answer. The first paradox or puzzle comes more or less from philosophy. It's a version of what's been called Parfit's teletransportation paradox. So suppose you are this guinea pig here, you're living on planet Earth, yeah? And every morning you go to your workplace on Mars. And since Mars is very far away, what you do is you enter a teletransporter. And this is a bit like in Star Trek. So the teletransporter scans you in all detail. And while doing so, destroys you basically. sends the information to Mars, and then on Mars builds a perfect copy of you. So this is very convenient, and you use it every morning to travel to Mars. But now suppose that one day there's a problem, there's a malfunction of the transporter. Yeah? So instead of just producing you on Mars, it actually produces two copies. Yeah? You will remain on Earth, but there will also be a copy that's produced on Mars. And suppose you actually know that. So you know that there's this problem with the transporter. And then before entering it in the morning, you ask yourself, well, what happens to me now? So will I remain on Earth, or will I go to Mars, or what will I see next? How should I think of that even? So you ask, what will I see next in this strange situation with this broken transporter? Could I put a probability perhaps on the two alternatives? And now arguably our laws of physics do not directly tell you how to put a probability on these two alternatives, for example, because we perfectly know how the world evolves. We know the physical laws. We kind of have a problem of the standard methodology to say where we are. And what does it even mean to locate us now? Now, a similar problem has actually appeared in physics, in cosmology, and that's known as the Boltzmann brain problem. I will really just sketch a cartoon version of it now. Let me just say that the cosmologists really write serious papers about this, and I'll also get back to that in the last part of the talk. So in a nutshell, here's the Boltzmann brain problem. Suppose you're in a really large universe. It's combinatorially large, so it's full of random processes. Think of thermodynamic fluctuations, think of quantum fluctuations. And now, since it's really large, then really many things will happen just by random chance. So for example, what will happen when you look up in this void here, you sit on your planet and you look up, then you know that somewhere out there, just by random chance, there will be copies of you appearing. Yeah? These are the Boltzmann brains. They just pop up with some made up memories just by random chance. They think they've lived this life on Earth like you did, but in the next moment, something strange happened to them and they disappear, okay? Now, how should you think of that? Suppose you know you live in such a large universe. How much probability should you put on the belief of being one of these strange fluctuations? Or in other words, when you ask, what will I see next? Well, what happens to me next? Will what happens to me next be whatever happens to these strange fluctuations? Or will it be business as usual as I think it should go on Earth or so? Now, the cosmologists are writing papers about this because they want to use this to exclude some cosmological models. For example, they say, oh, if you have a model and it predicts, you know, much more Boltzmann brains than actually evolved brains on planets, then you have a problem. And that would mean that you should believe to be one of these Boltzmann brains, so you should believe to disappear in the next moment. This is not happening, so the model is excluded. So this is something you find in papers by cosmologists, but again, the question is how you should think of that. Is that really the right way to think of it? And the problem again is that well, we know perfectly how the universe evolves, but we kind of don't know where we are. Wigner's friend is yet another example. So when we use the standard methodology, yeah, the quantum world evolves and now we pick out ourselves, we're sitting somewhere, want to use it to predict what's happening to us. First of all, it's not quite clear what we mean by the standard methodology here, how to use, for example, decoherence postulates or something like this. But when you do it, you run easily into apparent paradoxes as like Frauchiger and Renner have, for example, demonstrated in their paper. So maybe all this, so you know, we have all these puzzles and thought experiments, and the puzzles is always that we don't know how to answer the question, what will I see next in these situations? So I've talked about these three, but you can also ask, so this is very exotic puzzles, yeah? There's a very exotic regimes of questions you may ask. Another exotic question would, for example, be, what happens if somebody simulates you on a computer? Will you wake up in the simulation or something like this? But the question, what will I see next, is certainly a perfectly well-defined question. It's just in the ordinary regime of, say, laboratory experiments. So when you build up an optical table and we ask, will I see this detector click? Then this is not that exotic, and we typically know how we answer this question. Or for astronomical observations, we pretty much also know how to answer this question. So in this empirical regime, we think that physics applies. Yeah? Physics tells us how to answer this question. But we don't really know what to do in this exotic regime. Should we perhaps go for the philosophy of mind to find answers? But the problem is that some of these puzzles actually appeared in physics, in cosmology, for example. So there cannot be that sharp distinction between these two regimes. It's kind of a blurred distinction. And well, you may ask, well, what will I see next? Isn't that a strange question for a physicist? Isn't physics concerned with a different kind of question? Isn't physics concerned with the question, what is the world like? Instead, what will I see next? And then, well, not quite if you live in a quantum world. So the formalism of quantum theory tells us, what it tells us basically is the probabilities of the outcomes that we will see given our choice of measurements. And we know from Bell's theorem, for example, that it's even inconsistent to assume in some cases that measurements always tell us what the world has been like before the measurement, unless we give up notions of locality, for example. Just to make sure you're still seeing my slides and you're seeing Alice and Bob. Yeah?
Yeah, now it's perfect. Yeah.
Okay, good. Just wanted to make sure. Okay. So in summary, even physics tells us that this question, what will I see next, is somehow a natural question to ask. Okay. So then what I want to promise, want to suggest is that we should try to find unified approaches. We want a kind of unified approach that applies to both regimes at the same time. And in this sense, in some sense, that such an approach would generalize physics in a way. And that's at least a goal I want to advertise. It would be good to have such a thing. Okay, now what could such an approach look like? Let me give you a sketch of a kind of a toy approach, a kind of theory that tries that, and that already tells you perhaps how this can be accomplished. And this approach basically goes on by reversing the standard view. So here's again the standard view that I talked about. We have laws of physics that tell you how the physical world evolves, and we are somehow part of that physical world. And so our state, what we see, what we remember, and so on, follows just from the state and evolution of the physical world. Now, what I've shown you is that there are problems with that approach, at least for these exotic puzzles. This seems to be a methodologically inadequate view. At least it doesn't tell us how to solve these puzzles. And it's also in some sense conceptually hard to square with quantum theory. So my approach then is, my suggestion is to try and reverse the standard view. Let's say the laws of physics apply directly at the observer level or at the level of the locally available information. And let's just disregard the idea that there's a world around us, at least methodologically. Let's not talk about the world in the first place, at least for now. The idea is to say, well, what we want is we want some kind of probability of what happens next, given what happened now. So take your state at the very same moment, X, everything that you know now, that you remember now, that you see now. And in the next moment, you'll be in another state. And there will be basically a probability that tells you how likely it is to end up in one or another state. So the approach that there's a probability law that tells directly on the level of the observer of what's going on. This probability P in that approach will be universal probability. I will tell you in a slide in a second what that is. And the fun thing, perhaps surprising, is that one can show, and I will go to that if you assume this, that in the long run, the standard view will kind of emerge as a good approximation. In the long run, an observer that's so described will appear as if it was embedded into a larger process, which they may call the external world. Okay, so in some sense, in this approach, the external world would be a statistical phenomenon in some sense. Okay, so what is universal probability and how is this formalized? Again, this is a toy model. It's just the very simplest possibility you could try to formalize this idea. But here, I describe the states of the observer just as finite strings of bits. Yeah, think of zeros and ones. And at every moment, the observer basically learns a new bit. So the string grows one bit at a time. A very simple model. And you may ask, well, but that must be nonsense. I am not a bunch of bits. Yeah. At least when I use this description, I should say how I encode my state into zeros and ones. What's the data format? How should I do that? Good news is that it doesn't matter. So you can show that the theory that I'm going to present is independent of the choice of encoding. a little bit like general relativity is independent of the choice of coordinate systems. You'll see that. So think of your state as a bunch of zeros and ones. And now let's see what universal probability is. So this is a notion that goes back to several people, in particular to Ray J. Solomonoff from the 60s. The first notion you should think about is that measures on the bit strings. So a measure is basically a probability distribution on the strings. And the probability, if you see a string X now, the probability that you see a 0 next plus the probability that a 1 next should just be unity. Yeah. So you grow one bit at a time and you have a certain conditional probability of seeing zeros and ones, and this is normalized. That's a measure. Coin tossing would be, the mu of 0 given X would just always be 1/2 for every X. That would be a coin toss. Now, what's a semi-measure? A semi-measure is a bit of a more general thing. Probabilities don't have to add up to 1. So you can think of this as saying, well, next I will see a 0, or next I will see a 1, or if the thing will crash. So probabilities may add up to something less than 1. Now, what's an enumerable semi-measure? That's an important notion that shows up here in algorithmic information theory. Basically, that's a semi-measure that you can approximate with a computer program. So that's a semi-measure where there's an algorithm that takes as input X, the bit string X, and an integer n, and it outputs an approximation, mu n of X. And in the limit n to infinity, this is exactly the value that you want. And it's continuously growing. So you kind of approximate the value from below with a computer program. And if that's possible, then the measure is called an enumerable semi-measure. So what's a universal enumerable semi-measure? That's somehow a semi-measure mu. That's basically a mixture of all enumerable semi-measures. So you say that should be a thing, mu, such that for every other enumerable semi-measure nu, I find a positive constant so that mu of X is larger than or equal to this constant times nu of X. It's a bit abstract, but it really tells you that somehow this universal enumerable semi-measure mu is a mixture of all the others. It contains all the enumerable semi-measures with some probability in some sense. Now, when you normalize that thing, you get what I call universal probability. It's also called algorithmic probability sometimes. Now, this thing really has some fascinating properties, and you can look it up when you're interested in Solomonoff induction. It turns out that this probability measure gives higher probability to simple bit strings. So simpler strings have a higher probability than more complicated ones. And with simple here, I mean that these are strings that have a short description on a computer program. So think of the first billion digits of pi in binary. They are generated by a very short computer program, and so they have a very high universal probability. But if you just think of a million coin tosses of a random string, then this will have a very low universal probability. So in some sense, regularities get higher probability, and this makes that probability measure interesting for machine learning and philosophy, because you can use it to do universal induction in some sense. So when you just learn a bunch of bits and you want to predict new bits, then in many cases, universal probability is a good predictor. So I won't have time to go into the details of that, but that's called Solomonoff induction. So this is perhaps something that some of you want to look up if you're interested. Another way to think of universal probability is as some kind of natural a priori probability on the bit strings. When you say, instead of picking an arbitrary probability distribution, is there perhaps one that mathematics itself gives me? And then universal probability is in some sense a good candidate. All right, good. So let me give you postulates of a theory. The postulate is the following, that at every moment, and of course you can use the same postulates for you. So I'm in an observer state X, some bit string, and then I learn some new bits. And then a couple of moments later, I'm in an observer state X and Y are a couple of new bits. And this happens with universal probability P of Y given X. That's the probability law. So here is like a sketch. So Yeah, your observer state is you're sitting on the couch. Yeah, you're holding this pen in your hand, and perhaps you're Ernst Mach who actually draw that thing. You see this weight hanging from the wall, and you're kind of worried, oh, this is very loosely hanging there. And then a couple of moments later, perhaps the weight falls down and you feel some pain. Yeah? So then you have an observer state X in the beginning and another X prime later, and the universal probability that connects the two. Yeah? Of course, you want, so you think that the universal probability that the weight falls down on you is much higher than that you see perhaps the weight lift up in the sky or something like this. Yeah? So that's what we hope the universal probability can do for you. This is really a claim that this is a fundamental and objective private chance. So this is not rising from some kind of lack of knowledge or from some kind of unknown external world in which I would be embedded. So this is really, the view is that you as an observer are just a standalone and detached observer state. And this probability law is telling you what happens to you. All right. Now, I should say that this is really just a toy model. It's just an incomplete theory because I can say, well, I learn one bit at a time ad infinitum, but certainly sometimes there will be fundamental forgetting and information leaves perhaps is no more locally available and I forget a lot of things or so. That's not treated by this approach. So this is really just the first toy model, not a complete theory. Now, first claim, this is consistent with standard physics. In all situations in which standard physics gives you an answer, the answer that you find with this prescription is the same. Yeah. Only drawback is that universal probability is not computable, so you cannot actually use it to find the answer. It's sort of just abstractly, it would give you the same answer if you could compute it. So why is that? Basically, well, the standard view would tell you that you would compute physical probabilities, say, well, I kind of make a model of what I'm surrounded by. Perhaps it's a quantum process, and then I have kind of a wave function, and then I compute probabilities via the Born rule, and voila, probability 99% that the weight falls down or so. Yeah, in a very brief nutshell, the physical probabilities. But it can be guaranteed. It's guaranteed that in the limit of infinitely many bits, so if your observer state grows and grows, you learn more and more, then universal probability will actually converge to the physical probability with probability 1. Now, why is that? That's perhaps a bit surprising. So how does universal probability know about physics? Well, it doesn't really, but we know, according to certain physical versions of the Church-Turing thesis, or at least we believe, that the laws of physics, perhaps even those that we do not know yet, are computable in some sense. Yeah. In some probabilistic sense, at least, which tells you that in principle, the physical probability is computable in a Turing machine, even maybe not in practice, but in principle. And now Solomonov has proven that this is enough to guarantee that universal probability will converge towards it once you make a lot of observations. So this is really what's called Solomonov induction. So once you have collected a lot of data about the surrounding physical world, and you use universal probability, you get the same answers that physics would give you. Okay, so interpretation is somehow that asymptotically, your mind or the locally available information to you just contains enough information to basically reconstruct all the relevant aspects of the physical world for you. And then what universal probability does, it kind of detects these irregularities and assigns high probability to the fact that they remain present in the future, so that this conceived external world still dictates what's happening to you in the next moment. Now, interestingly, this is true without assuming that this external world actually exists. As long as you have made observations according as if there was such an external world, that will prevail in the next moment. Okay, now consistency with standard physics is good. That's certainly what we want, but it's certainly not enough. Yeah. It's not so surprising, perhaps, that now when you hold a large amount of information on a possible external world, that universal probability predicts probabilities that conform with that external world. But what happens before that? So why should you go there in the first place before collecting any information? Yeah. And without assuming that there is any external world to begin with. So I will now try to show you in a couple of slides that universal probability actually predicts some notion of external world. Certainly, what it does not predict is it doesn't predict most of the properties of this external world. So that's why it doesn't make it a theory of everything for sure. But it tells you that there's some kind of process that you see around you. To see that, you need to talk about candidate external worlds. And that's a definition that's a bit inspired by Rob Speckens. So here's a definition of a computational ontological model. So a computational ontological model at first is just a stochastic process. Think of some kind of world W that you can in principle simulate on a probabilistic Turing machine. And then you have a function f, a bit string valued random variable that points somewhere in that world, that kind of locates or reads an observer state from the world. That's a bit like in the standard prescription. We think of an external world, and then we somehow sitting somewhere, we can think of a function that reads out our state from that. And now once you have a probability distribution on the states of the world, this will induce a probability distribution on this random variable. So we get a resulting probability distribution on your observer state, which will be called mu W, the measure of the world W. Now this kind of formalizes the standard view also in that way. So you have this world at the bottom, it just evolves probabilistically over time. But if I just pick out myself by using this function, this reads out my state, then this evolves according to this marginal distribution, basically. Now, what you can now prove, so here's a theorem. We'll see step by step what it means, okay? Let me first read it. So if you're an agent subject to universal probability, then before you hold any information at the very beginning, or if you've lost all information in some sense, then there's a universal probability of at least 2 to the minus k of w that the ontological model of world W will be seen in the long run. So what does it mean to see a world W in the long run? Well, it means that, like in the picture above, the transition, what you see, you go from one state where the weight is hanging up there to the weight falling down by universal probability. That's the law that I've postulated. So the probability law is P of y given x. But in the long run, it will be very close to mu W of y given x. So it will be very close to the probabilities that world W would give you. So what is this world W that you get in the long run? Well, this is not determined. That's contingent. It's a probabilistic process. And every world has a non-zero probability, but simpler worlds have a higher probability. So if k of W, the description length of your world, is small, then it has a higher probability to, in the long run, determine what you see than if k of W is large. So again, so here's what I mean by that. So you have universal probability that, according to my claims, tell you the actual chances of what's happening to you. You have a candidate world, and the chances determined by this candidate world, that's mu W. And in the limit, they will get very close to each other. And this k of W is the description length of this computable world on a universal computer. So what this predicts, basically, it predicts that you see in the long run a probabilistic world W. And its complexity k of W is probably small. Now you can interpret this with a bit of goodwill as saying that this world W has simple laws of nature. It's like a short computer program that will tell you how it evolves. Now, we know that even simple probabilistic processes typically have very complex outcomes. So if you think of a coin toss, for example, the coin toss itself has a short description, but the actual outcomes 0, 1, 1, 0, 1, 1, and so on, they cannot be very much compressed. So very complex in the sense of algorithmic information theory. So the actual realization as seen by such an agent will typically be complex. But the measure here, mu W, will be computable, in fact. And that's the big difference to P, to the universal probability. Universal probability is not computable, but mu W is. So this means that it's an advantage to use mu W instead of P for prediction, because you can actually compute it. And now typically such processes start in a state of low entropy. And now if you look a bit around, see what have we found in physics, and that's very abstractly basically what we found. Yeah, we seem to be surrounded by a process that's abstractly probabilistic and computable, and that at some point seemed to have had a beginning in a very simple state. Yeah, so in a way that's broadly consistent with what we observe. Okay, right. Now, so far I've only talked about myself. Yeah, this is very unfortunate. One shouldn't do that. So I'm not a solipsist, right? So you can ask, what about more than one observer? What if you have like a second agent? What do different agents see the same thing or what? Like we haven't really talked about that so far. And that's a kind of fun thing that you see here. I will now show you how you should think of that and argue that you see some notion of objective reality as a kind of emergent approximation in such an approach. So how does that work? Think of some observer state that describes Alice the guinea pig, yeah? Whatever that is, yeah, she's happily sitting there, and her states that she sees, what she sees and knows and so on, looks pretty much as if she was embedded in a world. So a world is this world where you have to walk around and you jump up and you collect points. It's kind of a fun world, yeah? That's Alice's emergent external world that I've talked about in the last part. So everything looks for her as if there was this world around her. And suppose in a world, she actually finds another bit string valued random variable. So she looks around and points at, oh, there's this interesting thing over there that contains a lot of information. That looks like another observer to me. So then Alice may ask, or you may ask, does this thing B, this random variable here, represent somebody's first person perspective? And I ask, what do I mean by this question? This isn't a technical question. This sounds like a philosophical question, but here you can ask it in a technical way. You can compare two probability distributions. So here's what I call P third, the third person probability. So that's the probability that tells you how the state of B changes over time according to the laws of a world. A world is a probabilistic world, so whatever happens to that Bob thing sitting there has a well-defined distribution on it. That's P third. But then you can also say, well, what is the actual first person probability if you're in Bob's shoes, if you are Bob? And my main postulate has been that this is universal probability. So this is universal probability P. This is like the first person probability. And now a priori, these are two different things. The first person probability tells you, like, if you are Bob, what happens to you? And the third person probability is like, if you're Alice and you see that thing over there called Bob, then what do you think that should happen to that thing? Now here's a simple example. Suppose that every morning the sun goes up in a world. And so Alice knows she has a really high chance, 99%, of seeing the sunrise tomorrow. Yeah. Then Alice also knows that she has a 99% chance of seeing Bob see the sunrise tomorrow. But you can ask, but what will Bob's actual chances from his perspective be to actually see the sunrise? So here you have this P third is like what Alice sees Bob seeing, and P first is the probability of Bob will actually see. And a priori, these could be different probabilities. But fortunately, you can prove a theorem in that approach. As long as that Bob thing over there contains enough information and keeps accumulating more and more, these probabilities are very close to each other. So the first person and the third person probability the difference tends to 0. So in a way, if Alice sees Bob see the sunrise, then Bob will also see the sunrise. In a sense, a world is not only a world for Alice, but also for Bob. So this is some notion of objective reality as a provably statistical phenomenon in some sense. But of course, every theorem has some premises, like things that must be satisfied for it to be true. And if these conditions are not satisfied, then these P first and P third will be different things. And this could be the case, for example, if Bob doesn't hold enough data, or if he forgets a lot by accident or so, then P first and P third will be very different. In this sense, Alice might call Bob a probabilistic zombie. That's what I call a probabilistic zombie a bit according to Wittgenstein. And that's a pretty counterintuitive thing. Let me tell you one slide about probabilistic zombies. Let me begin with a very boring case of a probabilistic zombie where the first and the third person probability disagree. Yeah. So observer states, I've often used them colorful as a description of what you are or what's available to you, but in principle, they're just a bunch of zeros and ones. Yeah? They need not be related to humans or guinea pigs or anything. So what you can think of then is an Alice in her A world, she can simply produce 2 copies of a piece of information and put them on 2 different places and force them to evolve differently. So this means that the physical probability of what happens to them next differs. And so at least one of the 2 instances must have a first-person probability different from Alice's third-person probability. It's kind of a very boring case of where these probabilities disagree. And we have kind of probabilistic zombie. Here is a more disturbing case. I'm not normally reading long texts, but let me just give you that as a kind of science fiction fun scenario, okay? Suppose Alice runs a cellular automaton on her supercomputer for a couple of hundreds of years. And then what happens is in this game of life, or whatever she does, evolution starts. And after a long while, agents show up, including an agent called Bob, who explores his cellular world and wonders about the meaning of it all. Now, where do I come from in this kind of Terry Pratchett-like scenario? Yeah. And then what Alice does suddenly is she intervenes in the simulation and changes its laws all of a sudden. And then what you find is at this point, P first and P third will start to disagree. P third is the new probability law that Alice has imposed, and P first will basically be the continuation of the old probability law. So what you find is that Bob's mind, in some sense, will leak out of the simulation, and it will be replaced by some kind of unlikely copy of Bob, which is something like this medieval idea of a changeling. Yeah. Now, I've put up this picture here mostly because I know how to model that mathematically, but I don't know how to give you any intuition on that. It would be an extremely counterintuitive phenomenon. Now, counterintuitive and perhaps disturbing, but the phenomenon really helps us to dissolve the puzzles that I've talked about in the beginning. So let me now in the final part go back to the Boltzmann brain problem and tell you how this is dissolved in that approach. So here's again the Boltzmann brain problem. Assume that Alice, the guinea pig here on planet Earth, lives in an extremely, extremely large universe, like, 10 to the 10 to the 10 to the 100 in whatever unit you want to put on it. And then you have a large number of brains, quote unquote brains, that just pop up with false memories, fluctuate into existence very briefly and then disappear, or something else strange happens. Now suppose Alice knows that and she thinks she sits on this planet, but she's not sure anymore. She may ask the following question, given what I see and what I think I know, am I the guinea pig here on this planet, or am I one of those strange Boltzmann brain quantum fluctuations? Now, what's the standard answer that cosmologists like to give? Standard answer would be to say, well, Alice, be a good cosmologist and try to count how many Boltzmann brains there are out there, and compare this to the number of standard guinea pigs on planets like you think you are. And if there are far more Boltzmann brains than standard guinea pigs, then you are probably a Boltzmann brain and you will soon disappear. And again, since we are not disappearing, then cosmologists would perhaps want to say this as an argument that perhaps the universe is not that large. Now, if you take an approach like the one I've shown you, an idealist approach, then this would not be the right answer. Instead, the answer would be that the question itself is meaningless. You are just your observer state. So you are just detached structure. You're all the memory and what you see, all this locally available information. But it's not that this information would have a property that it sits here or sits there. So it doesn't even have a property called position. So in some sense, you are all these Boltzmann brains and you are the planet guinea pig all at the same time. So the question itself is meaningless. But then you say, okay, well, fair enough, but then what happens next? So fair enough, but what happens to me next? Will it be business as usual on Earth, or will it be one of these strange Boltzmann brain experiences? And then the answer here in that idealist approach would be, yes, this is now a meaningful question. What you have to do is you have to compare the universal probabilities that your next experience Y is a Boltzmann brain, with Boltzmann brain information, YBB, and not why Earth. So you compare the universal probability of these two scenarios conditioned on what you hold at the moment. And now what you need to know about and recall about universal probability is that it encompasses, that it embodies Occam's razor. So strings Y, the next information Y that's more compressible has a higher probability. But this means that business as usual will probably be what's happening to you, because if you just make experiences and collect information as you did before, and things just go pretty much on like they did before on Earth, then what you see is more compressible. Whereas if you just see random noise, like, yeah, I mean, you would have to be more careful, but the idea is that making one of these strange Boltzmann brain experiences next would be less compressible and more complex, and is thus less likely. So business as usual will prevail. And it doesn't matter how big the universe is. It doesn't matter how many Boltzmann brains are there. It would be bad news in that sense for cosmologists. All right, so I'm at the end of my talk. So here's a summary, kind of what I've shown you. So I've shown you some conceptual puzzles that motivate, as I argue, a kind of idealist approach in some sense to the foundations of physics. Again, this has nothing to do with consciousness or so. It's more about absolute locality or locally available information in some sense. And quantum theory motivates this as well. Now, I've shown you a kind of incomplete toy model or theory of this kind, which is based on universal probability, algorithmic information theory. It predicts in some very abstract sense that observers so described see a simple computable probabilistic external world around them. And one can understand objective reality as a kind of excellent approximation, like a statistical phenomenon that tells you that the usual view of the world is still a very good approximation to that kind of view. It dissolves most of the conceptual problems and predicts a couple of interesting new phenomena, like these probabilistic zombies, perhaps. So you can see you can find the paper just published in the Quantum Journal. Now, name of the journal, Quantum. I haven't talked much about quantum theory because I didn't want to overwhelm you with too much stuff. Two things about that. First, what I said is in principle compatible with quantum theory. So my definition of a computational ontological model could also be a quantum computation. And I believe that it also predicts some aspects of quantum theory as consequences of such a view. Maybe no signaling, but the violation of Bell inequalities in some cases, but that would be a longer story. And whoever is interested might just have a look in my paper where all this crazy stuff is written up. Okay, that's it. Thanks very much for your attention. Thank you.